Hello students, welcome to my channel Arun's Physics Portal. In this lecture, I will discuss about the shell and electromotive force. This topic is meant for class 12 students of CBSE, ISC and different state boards. This will also be found useful for various competitive exams like NEET and JEE Mains. The complete note of the topic is given here for your convenience. I hope you enjoy going through it. Now let us come to the topic. Shell and electromotive force. A shell is a simple device that provides the potential difference necessary to maintain a continuous flow of electric current in an electric circuit. It consists of two dissimilar metals, for example, copper and zinc rods or plates, which we call electrodes. They are partially immersed in a chemical solution, which we call electrolyte, which may be dilute sulfuric acid. This is shown in figure 1 here. When the zinc rod is immersed in sulfuric acid, zinc ions enter into the solution, forming zinc sulfate, and electrons accumulate on the zinc rod, making it negatively charged. The two atoms of hydrogen carrying 2 units of positive charge are released for every zinc ion that enters into the solution. The hydrogen ions transfer their charge to the copper rod, making it positively charged. The complete chemical reaction between zinc and sulfuric acid is as follows. We show here you the complete chemical reaction between zinc and the sulfuric acid. The more mobile electrons stick to the zinc rod, thus making it negatively charged. When the two electrodes are connected by an external resistor, as shown in figure 1, the hydrogen atoms carrying the positive charge travel to the copper rod and transfer the positive charge to the copper rod, thus making it positively charged. The copper rod is at a positive potential of 0.46 volt with respect to the electrolyte, and the zinc rod is at a negative potential of 0.62 volt with respect to the electrolyte, as shown in figure 2. The total potential difference between the two electrodes is thus 1.08 volt, which is the EMF of the shell. When the two electrodes are not connected externally, chemical reaction takes place inside the cell till a potential difference of 1.08 volt is set up between the electrodes. When the two electrodes are connected through an external resistor R, electrons flow from the zinc rod to the copper rod through the resistor R and neutralizes the positive charge on the copper rod, and fresh zinc ions enter the solution to maintain the potential difference between the electrodes. Okay. In figure 2, we have shown that the copper rod is at a positive potential of 0.46 volt with respect to the electrolyte, and the zinc rod is at a negative potential of 0.62 volt with respect to the electrolyte. The total potential difference between the copper and the zinc rods is thus 1.08 volt. Okay. The simple cell described above is the voltaic cell, also sometimes called the galvanic shell, after the 18th century Italian scientists Alessandro Volta and Luigi Galvani. When a charge Q moves from the higher potential to the lower potential through the external resistor, its potential energy decreases. And to maintain the flow of charge, the cell again brings back the charge Q from the lower potential to the higher potential. Thus, work is done by the electromotive force of the battery. This is similar to the function of a pump shown in figure 3, which pumps water from a lower level to a higher level. So this is the pump here. This is a jar where we have water. This pump lifts the water in the tube, which falls from P to Q. As it falls from P to Q, its potential energy decreases. The pump again raises water in the tube and the process continues, and the flow of water continues in the tube. So in the figure 3, when water falls in the vertical tube from P to Q, its gravitational potential energy decreases as the pump does work in raising water from the lower level to higher level to maintain the continuous flow of water in the tube PQ. Similarly, the electromotive force does work in displacing the charge Q from Q to P through the shell. Okay, we have P plate of the shell at a higher potential and Q plate at lower potential. So the electromotive force does work in displacing the charge Q from negative plate to the positive plate through the shell. The EMF of a shell is defined as the work done by the shell in moving a unit positive charge once around the whole circuit, including the shell. If W be the work done by a shell in moving a charge Q once round a circuit, including the shell, then the EMF of the shell is defined as E equal to W upon Q. This equation 1 can also be written as E equal to 1 upon Q integral of dW over the entire cycle. So dW is the small work done. So this is force into displacement. So if E is electric field and Q is the charge, so force is Q into E. So this is Q E dot dl. Okay, so this Q cancel with this Q and this is integral of E dot dl, where the integration is carried over the complete loop. The unit of EMF is joule per coulomb, which we call volt. A cell can thus be thought of as a seat of EMF and not as a source of electric charge. This should be clear to you. According to the modern theory, a seat of EMF, also called the source of EMF, converts some form of energy such as chemical energy, thermal energy, radiant energy, or mechanical energy into electric potential energy. When a cell is connected between 2 points, a potential difference is set up between those 2 points. When an external resistor R is connected across the 2 terminals of a shell, charge flows from the end P to end Q, that is from higher potential to lower potential, or in the direction of electric field in the external circuit. However, inside the shell, charge flows from plate Q to plate P, from lower potential to higher potential, or in the direction opposite to the direction of the electric field. The EMF of a shell in a circuit is taken to be positive if the current flows through the shell from the negative terminal to the positive terminal, and negative if it flows from the positive terminal to the negative terminal. The net EMF in a circuit with 2 cells is shown in figure 4. In figure 4a, we have 2 cells of EMF E1 and EMF E2. Current flows from the negative plate of this shell to the positive plate, and in the second shell also it flows from the negative plate to the positive plate. So both E1 and E2 are taken to be positive. So the net EMF of these 2 cells is equal to E1 plus E2. In figure 4b, in the shell of EMF E1, the current flows from negative plate to positive plate. So E1 is to be taken to be positive. In the second shell, the current flows from positive plate to negative plate. So E2 is taken to be negative. So the net EMF of these 2 cells connected in this fashion is E equal to E1 minus E2. In figure 4c, the current flows from the negative plate to positive plate of this shell. So E2 is taken to be positive, whereas the current flows through this shell from the positive plate to negative plate. So E1 is taken to be negative. So the net EMF of these 2 cells is equal to E2 minus E1. Clear? Internal resistance of a cell. Resistance is the obstruction. Okay. So resistance of a conductor is its opposition to the flow of current through it. Similarly, a shell has also a resistance known as its internal resistance. So the internal resistance of a shell is its opposition to the flow of current through it. It is denoted by a small r and depends on the nature of the electrolyte and the electrodes of the shell. Okay. Now let us see what is the relationship between the electromotive force, the potential difference between 2 points, and the internal resistance of a shell. See in figure 5, we have a resistance R. To measure the potential drop across it, we have a voltmeter across it. You know that voltmeter is always connected parallel to the resistance. Okay, we have a shell of EMF E of internal resistance small r, and this is the ammeter connected to measure the current through the circuit. Okay, so if I be the current flowing in the circuit, then by Ohm's law, let the current be I. Then by Ohm's law, we have I equal to E upon capital R plus small r. The resistance R and the internal resistance of the shell small r are in series because the same current flows through both of them. So they are in series. So current is total EMF upon total resistance in the circuit. This is R plus R, or E equal to IR plus I into a small r. Or we can write E equal to V plus IR, where V equal to IR is the potential difference, also called the potential drop, across the external resistance R. This is also the potential difference between the terminals of the shell, and this is also known as terminal voltage or terminal potential difference. The terminal potential difference or terminal voltage of a shell is thus the potential difference between its terminals in a closed circuit when a current is being drawn through the cell. Equation 3 gives you the relationship between E, V and R. When a shell is connected across an external resistance, a part of the EMF, that is E minus V, is used up in overcoming its internal resistance R. This part of the EMF, therefore, does not contribute to any useful work and hence is known as lost volt. So lost volt is EMF E minus V, and that is equal to I into small r. Okay. So remember the following points. When the cell is discharging, that is, when the current flows through the shell from its negative terminal to the positive terminal, as shown in figure 6a, the potential difference or the terminal voltage across it is V equal to E minus IR. Okay, this is the potential difference across the resistance R. This is V equal to E minus IR. IR is the potential lost when the current flows through the shell. So here V is less than EMF. Okay, when the cell is being charged by an external voltage source, as shown in figure 6b. So this is your figure 6b, where we are charging the shell of EMF E and internal resistance R by an external voltage source V. Okay, and let I be the current supplied by this applied voltage source. By Kirchhoff's voltage law, the sum of all the potentials in a closed loop is always zero at every instant of time. So if this is a closed loop, then the total potential drop in different parts of the circuit always add up to zero. So here the current flows from negative terminal of the source to the positive terminal. So this is voltage is taken to be positive. Okay. So this is your V. Clear? Now here the current flows from the positive terminal of the shell to negative terminal. So this is taken to be negative. So this is minus E. Okay. The current I flows through the cell from its positive terminal to negative terminal, and this is the resistance R, the internal resistance of the shell. So the drop across this resistance is equal to minus I into R. Okay, this is negative because the current flows from the positive terminal of the shell to the negative through the shell. So this is minus I into R. Okay, this add up to 0 according to Kirchhoff's voltage law. So from here we get V equal to E plus IR, or this gives you V greater than EMF E. Okay, when a cell is in open circuit, that is, it is not connected to an external resistor as shown in figure 7a. We have no resistance here connected, so this is an open circuit. So R is here infinite. There is no current through it, and equation 3 reduces to V equal to E. In other words, when a cell is in open circuit, its terminal voltage is equal to its EMF. In this case, the external resistance between the terminals of the shell is infinite, and therefore the current I equal to E upon R plus R, and because R is infinite here, this is E upon infinity plus R, so this is E upon infinity, so this is 0. Okay. When a shell is short circuited, that is, the external resistance between the terminals of the shell is 0, as shown in figure 7b. This is your figure 7b. The current through the shell is maximum possible, and is I equal to E upon R plus R. R is here 0, so this is E upon R. The terminal voltage in this case is equal to simply V equal to IR, because R is 0 here, this is 0. Okay. Difference between EMF and potential difference. Following are the differences between the EMF of a shell and potential difference. The EMF of a shell is the maximum potential difference across its terminals when the shell is in open circuit. Second, the EMF of a shell is constant and is independent of the resistance in the circuit, whether external or internal. It depends upon the nature of the electrolyte in the shell. The potential difference between any 2 points in the circuit depends on the resistance in the circuit and the current flowing in it. A source of EMF in a circuit is required to maintain the flow of current in it. And when a current flows in the circuit, there is a potential difference between any 2 points in the circuit. So we can say that EMF is the cause, whereas the potential difference is the effect. Okay, so this is all about the shell and the EMF. I assume you like this presentation. यदि आपको मेरा यह प्रेजेंटेशन अच्छा लगा हो तो इसे लाइक करें, शेयर करें और मेरे चैनल को सब्सक्राइब करें. So thank you for watching. See you next time with some other topic of interest. Till then, goodbye.